Hey everybody! In this video, we discuss hyperparameter optimization for neural networks using KerasTuner, which is built on top of Keras and can be used for identifying suitable hyperparameter configurations. But what are hyperparameters and why we just don't call them parameters? Hyperparameters, you can think of them as variables that control the training process as well as the structure of a machine learning model, or in general, in this case, a neural network model. And the reason that we call these hyperparameters is because we have to set them before the training process begins. To better understand this, recall that when you have neural networks, you have weights and biases, and you learn them during the training process using backpropagation. However, hyperparameters are those parameters that we have to set them before the training process starts. This can be the number of hidden layers, the number of neurons per layer, the learning rate, and so many other variables. And hyperparameters, they have a significant impact on the model's performance. So therefore, it is critical to be able to set these hyperparameters to appropriate values. So in general, we have two types of hyperparameters. One is model hyperparameters. The other one is algorithm hyperparameters. For model hyperparameters, these are the ones that they determine or affect the architecture of a model, right? The number of hidden layers, the number of neurons per layer, and so on. For algorithm hyperparameters, these things influence the learning process itself, such as the learning rate and gradient descent, which is a very important factor when you update the parameters in your model, the regularization strength that you choose, and also in some cases, you can have like momentum or not use momentum during your stochastic gradient descent, even batch size. These are all algorithm hyperparameters. So we have to be able to, in general, to identify appropriate hyperparameters for both your model and in terms of the training algorithms that you use. There are several common techniques for hyperparameter optimization. The easiest thing you can always do is grid search, which means that you define a grid or set of possible values for each hyperparameter. And then the algorithm that you have in terms of hyperparameter optimization evaluates every single combination to find the best one. Although this is the simplest thing you can do, it's also extremely computationally expensive. And to understand this, let's say you have 5 hyperparameters, and each hyperparameter can take on 10 different values. Therefore, in this case, if you want to count the total number of possibilities, it's 10 to the power of 5, which is 100,000 combinations. And let's say even if trying one combination takes, let's say, a minute, now it means that you have to wait 100,000 minutes to perform a full grid search. Therefore, in practice, this is not really practical if you want to perform a thorough hyperparameter optimization. An alternative is to use something called random search, which means that instead of exhaustively trying every possible combination, your random search method samples a predefined number of configurations from the hyperparameter space. So this means that if, again, think about the example I just mentioned about having 100,000 total combinations. Now you say that, well, my budget is only to perform 100 configurations, or to evaluate 100 configurations, and therefore you sample 100 out of the 100,000 samples, and you hope that that will give you a good idea of the best performing hyperparameter. So therefore, this is more efficient than grid search for sure, but it does not guarantee that you will find the absolute best combination. Therefore, there are some other techniques that are trying to do something smarter than grid search or random search. And one of these techniques is Bayesian optimization, where you use a probabilistic model to learn the relationship between hyperparameters and model performance. So in this case, you really want to learn how these hyperparameters impact model performance and use this information to optimize this relationship between hyperparameters and model performance. But the downside is that this is somewhat complex to implement because you have to use a technique usually called Gaussian processes, which also has its own hyperparameters. And also you have to choose something called an acquisition function, which tells you which combinations you should try next, because we don't want to do this randomly. We want to use this based on this relationship between hyperparameters and model performance. Therefore, Bayesian optimization, although it is very powerful, you have to make some decisions about the choice of your probabilistic model, how you want to select new configurations to try and evaluate, and so on. And there's also another alternative, which is known as Hyperband. This is very also popular and common in neural networks and in machine learning. And the idea is that we can use something called an early stopping technique to better allocate resources. What this means is that we can start with almost all configurations that we have in our hyperparameter search space. And then once we find out that some of them are not performing very well and they're performing poorly, we can discard them and terminate them and then allocate our budget to the ones that are more promising. So it's a kind of like a very smart way of being able to figure out, well, where we have to allocate our resources to get the best out of our investment, right? And so in terms of hyperparameter optimization, it's a very rapidly evolving field, and there's still a lot of research in this area. And unfortunately, the coverage of this topic in most textbooks is either non-existent or very limited. But the good thing is that a lot of research articles that they provide a lot of useful information about these critical aspects of machine learning and neural networks. And for a comprehensive review, I recommend you to read this paper, Hyperparameter Optimization, Foundations, Algorithms, Best Practices, and Open Challenges. This is a very thorough and comprehensive paper that was published in 2023. You can look at this webpage. It's open access, so you shouldn't have any problems with downloading this paper. And therefore, my suggestion is to go through this paper to get a really good sense of the field. But in this video and in this notebook, the goal is to give you a quick snapshot of these methods that I just mentioned, and more importantly, show you how you can use KerasTuner for implementing these hyperparameter optimization techniques. KerasTuner is not automatically installed when you install TensorFlow and Keras, and you have to actually use pip install KerasTuner to add this library into your notebook. So you run this pip install KerasTuner, and in order to make sure that you install this correctly, you can always just run this cell, import Keras_tuner as KT. That's the common abbreviation we use, and then use the version here. So the version that I have is 1.4.7. Okay, so in order to be able to use KerasTuner, it's important to understand a little bit the math behind hyperparameter optimization and some of the technical details. So let's first go through those topics, and then we will talk about KerasTuner. So in a machine learning problem, the goal is always to find a machine learning model that I call this f hat, which is obtained by configuring its hyperparameters. And that hyperparameter I can show here using this lambda, which belongs to a hyperparameter search space. And we train it on some data. So in other words, the way that you can find a machine learning model is to have some data and then also set these hyperparameters. This can be, for now, let's say, just the number of hidden layers in a neural network model. And then you can solve the empirical risk minimization problem to find f hat and its associated parameters, right? So that's the typical empirical risk minimization for model fitting. However, what we know is that for every machine learning model, we should not evaluate its performance on the data that we have seen. So instead, we should always have some unseen test data that we can use to find an unbiased performance estimate. And therefore, instead of just working with one data set, we need to at least have two data sets, D-train and D-test for training and testing. And what's happening here, in order to understand this equation, we use the training data and this hyperparameter configuration that we have lambda to find this machine learning model f hat. So in order to find this, we do the empirical risk minimization. And now for some test data points, we're going to measure the difference between predictions and the true outputs, right? So this X and Y here belong to the test data set. And in general, you would like to find the expected value, but if you have a finite data set, then you replace this with an average. And in this case, this L quantifies the prediction error, right? Such as mean squared error, cross entropy loss, and therefore the goal is to minimize this as much as possible, find the smallest possible value for generalization error. And the idea behind hyperparameter optimization algorithms is to find the best performing hyperparameter configuration for a machine learning model on a given training and testing data set. And the search space in general contains all possible hyperparameters for each of these, like, let's say L hyperparameters that we have. So what this means is that, let's say in a problem, in a neural network model, you want to find the optimal value of the learning rate, batch size, activation function, number of units, number of hidden layers, right? So you have, in this case, 5 different types of hyperparameters. So you have lambda 1, lambda 2 to lambda 5. And you have to, specify ranges for these like hyperparameters. For example, for learning rate, you can say that, well, this can be anywhere from 10 to the negative 6 to 10 to the negative 1. You can use log scale if you want. In this case, it makes sense to use a log scale than a linear scale. You can also use like a batch size, which is like, 2 to the power of 2 to 2 to the power of 6, right? So you consider different options for batch size, for activation function. It's categorical, but still works, right? So in this case, you have like 4 different types. So that's something that you can include, or the number of units, number of layers. These are integers, obviously. And you form your search space. So this is an example here, but you can always create something like this for your own problem. And this means that now you consider all possible configurations. That's your entire search space. And your goal is to find the minimum value of your generalization error across the entire search space. So ideally, you want to be able to solve this problem, except the fact that the problem is that this is probably a complex optimization problem, because this C lambda, and C lambda here is what I use to summarize this entire thing here, right? This generalization error. Obviously, you can plug in the whole thing here, but I wanted to make sure that it's easier to understand what is happening. So this generalization error is a function of lambda, and now we want to minimize this with respect to lambda. And since this does not in general have a closed form expression, this is a kind of like a difficult optimization problem to solve. And most techniques are based on just evaluating different values of lambda. So we plug it here into this optimization problem and see which one gives us the best possible result, which in this case, since it's a minimization, which one gives us the lowest possible value. So grid search and random search are very easy topics to understand, right? So grid search is the one that you evaluate all possible configurations. Random search is the one that you only consider a predefined number of configurations and you do sampling. And in order to, kind of like show you the difference here, I wrote this code here that I said that, well, I have 2 hyperparameters. Let's say, they can take values from 1 to 9, and I want to consider 4 different values for each one, right? So in this case, you get 16 different combinations if you do a grid search. But with random search, what you really do here, let's say we want to do the 16 combinations, but we now choose them randomly in each interval. So the nice thing here with random search is that for example, if you look at HP1 or hyperparameter 1, you're considering more distinct values of HP1. it's not as uniform and I would say structured as the grid search, but the nice thing is that you're considering more combinations. However, the downside is that there are areas that we don't know very much at all about those regions, right? Whether what happens if HB1 or sorry, HB2 is between 4 and 6. That's kind of like a blank space that we don't know. And that's something that, more advanced, techniques, they can address that. Okay, so now let's look at Bayesian optimization, one of these more advanced techniques to address the problem that we just mentioned. And the idea is that Bayesian optimization is a probabilistic model-based optimization technique, and it's very useful for optimizing objective functions that are expensive to evaluate. And in this case, we form a probabilistic model, usually a Gaussian processes that approximate this, objective function, meaning that we want to directly map this function between lambda and C lambda. And once we have that, that's very helpful because now we can actually directly solve the optimization problem. Something very important with Bayesian optimization, since we are now talking about the big picture, is this choice of acquisition function. So what this means is that when you're using Bayesian optimization, we have, let's say, 10 different configurations of hyperparameters that we have already evaluated. So we know exactly the values of C lambda. So now we use this information to map this lambda to this C lambda. And there are parts of this space that we are not so confident about, meaning that we have higher uncertainty. So therefore, this acquisition function tells us which areas are more important, like which areas we have to sample more. But this is not just enough, right? Because if we just focus on areas that we are not very confident, still we are maybe missing information about some areas that are very far from known samples. And that's the idea behind this general topic of exploration versus exploitation, right? So exploration means that you want to sample in areas that, they're kind of blank, you don't know very much about them. And exploitation means that sampling areas that you have good knowledge about them and you want to know more about those areas. And therefore, overall, the key idea here is that you want to find a mapping between lambda and C lambda, and at the same time be able to find a measure of uncertainty, which areas we really need to know more information for them. And in this case, also I have some code that uses this Gaussian process regressor. I don't want to go too much into details of this in this video because that's kind of beyond the topic of hyperparameter optimization. But what is really important is this figure that we get here that explains how it works. Let's say you only have one hyperparameter and you have evaluated the values of C lambda for 1, 2, 3, 4 data points, right? These four red circles here. And you want to choose a new configuration to see whether that gives you a better result or not, right? Because based on these four existing results, you're saying that, well, it looks like if I increase my hyperparameter value, then I should get a lower value of C lambda. Is that true or not? Okay. So in this case, use this Gaussian process regression, which gives you this information about the variance of the predicted values or the confidence interval. And you can see that, well, we are not sure at all what will happen if we get far from this hyperparameter value 4, especially in this case, if let's say the max is 6, we have the highest amount of uncertainty here. So in this case, that's the next point that we are going to evaluate. So you're going to plug in this value of hyperparameter, train your model, measure the generalization error, and see what that gives us. And based on that, now you can make decision whether that's the best or the lowest possible value for C lambda, or you have to search more. So this really explains very well this idea behind Bayesian type optimization. The next technique that I want to cover here very quickly, and this is what our Keras Tuner example is based on too, is this idea of hyperband using successive halving. So what is hyperband? So hyperband is designed to optimize hyperparameters, by dynamically allocating resources to promising configurations and getting rid of less promising ones. And this method or algorithm uses something called successive halving, which involves running multiple configurations and progressively eliminating those that they perform poorly after a fixed number of iterations. And this makes sense for neural networks because here iterations means typically the number of epochs, which means that we have these four stages. We are going to generate a large number of random hyperparameter configurations from your entire search space. You're going to, you know, train each configuration for a small number of iterations or epochs and see, you know, in terms of the generalization performance, you know, which ones they do better. So you have like a ranking of them. And after this step, we're going to eliminate the worst performing configurations, means that we are not going to continue training them. And instead, we are going to allow those more promising ones for more iterations or epochs, right? So we want to kind of like fine tune them more while getting rid of the ones that we think that they're not going to do well at the end. And overall, we repeat this process with the number of configurations have and the resource allocations to the best performing configuration. So this figure here explains this very well. So let's say hypothetically, you have all these like 8 different models and their validation loss or C lambda as a function of number of epochs. And again, let's say hypothetically, we can run all of these for 100 epochs. We can afford to do that. So you can see that if you just look at everything up to epoch 20, it looks like this very first curve that we have is not going to do very well compared to these like ones that we have here, right? Because these are doing much better in terms of the generalization error that we have, right? So the idea is that, well, let's just get rid of these, you know, top few ones here, which means that they are the worst because we want to minimize the value of validation loss. And now let these, you know, more, you know, promising ones to continue training, right? So here it's hard to see these, but you can basically ignore these 2 or 3 curves that you have on the top because they're not promising. And so now this allows you to do like, let's say 40 epochs for these like top performing ones. And again, you do the same thing. You're like, well, these ones, they don't do very well. Let me just focus on these like, you know, top performing ones. And you continue this until you have only a few top models that you're looking for. So this is a very smart idea in terms of trying to predict which configurations are not promising and getting rid of them. And this makes a lot of sense for neural networks because you are have this, you know, important thing number of epochs, which is really what affects the amount of time and resources that you have to spend on training your model for different configurations. So we can allocate that in a very smart way. Okay, so now let's look at an example using KerasTuner. So we're going to import TensorFlow as TF. From TensorFlow, we're going to import Keras, and then we import Keras underscore tuner as KT, right? So that's like the new thing we are using, this Keras Tuner. And we're going to look at the fashion MNIST dataset. This is built in. So from Keras, the datasets.fashion MNIST, we're going to import the training and testing data. You can see that the training data has 60,000 images, 28 by 28, and 10,000 testing images. We have our, you know, labels for the training data. They're from 0 to 9 for the 10 digits. Something that it's always a good idea to do is normalizing or pre-processing your inputs. We're gonna convert them to floating point numbers, dividing them by 255, so that these inputs are from 0 to 1. The most important part about KerasTuner is having this thing called hyper model. So a hyper model is a model you set up for hyperparameter tuning. That's why it's called hyper model. And includes both the model architecture and what hyperparameters you want to sample from, meaning that, you know, you have to define your entire hyperparameter search space, very similar to what we just explained here, right? So you have to explain this within your hyper model. So we define a function, call this model builder. Of course, you can call this anything you want, but this is like the common name that you see like, in TensorFlow and Keras. So we define this model. It accepts the hyperparameters, right? That's the HP. And now you define your model. You say that it's a sequential model. You flatten the input so you have a one-dimensional input because you want to use fully connected layers. And here is the main part. So you want to, let's say, tune the number of units in the first hidden layer. So you use hp.int because that's an integer. So for integers, use hp.int. For floating point hyperparameters, for the ones that they belong to a set of discrete values and if they're Boolean values. So these are 4 types of hyperparameter types that you can have. And you set the minimum value, the maximum value, and the step size. And once you just give this a name, so here we call this HP underscore units, now you define your normal dense layer, but you just say that this units is this HP unit. So now Keras knows that, well, this doesn't take only one value, it's actually a bunch of values that belong to this range. And here we set also the activation function. And finally, we use our last layer for classification. Since it's a 10 class classification, we use 10 neurons. To make this a little bit more interesting, we also want to adjust the learning rate. For that, we use hp.choice because I want to choose one of these 3 values, right? So 10 to the -2, 10 to the -3, 10 to the -4. And you can see that the only thing you have to do is that once you define this variable or object, I would better say object, you pass this as the learning rate for the Adam optimizer. And after that, you just define your cross entropy loss function and the metric that you want to use. So that's all you have to do. In this case, we have 2 hyperparameters we have to tune, HP units, HP learning rate, and we define the entire search space. Okay, so then the next thing is where you want to choose the algorithm or the technique you use for your hyperparameter optimization. You can use random search, you can use Hyperband, Bayesian optimization, or sklearn if you want to use something from scikit-learn. But for now, let's use Hyperband. I really like this because it's a very nice and easy to understand method based on successive halving that we just discussed. And the full documentation is here, so you can just click on that link and you can see that, all the parameters. The most important ones is that first you have to provide a hypermodel, the one that we just defined, which is here, the model builder, right? So that's exactly for what we just did here. And then you also have to define the maximum number of epochs that you're willing to train each model. There are a few other parameters here too that you don't have to necessarily adjust them if you're not familiar with these. The main thing here is that I set this max epochs to be 5, which is the maximum number of epochs to train when you're doing your hyperband optimization technique. So I've already run this cell because I want to make sure that we don't have to spend too much time here. So in this case, you define your tuner and then you use tuner.search. And this is very similar to model.fit. You provide your training data, the number of epochs, and the validation split, right? And this epochs is the number of epochs used for your best model, right? So that's why your 2 different epochs here. This epoch is the one that you use for Hyperband, and this is the epochs that you use for your best models. So you can see that here we have multiple trials, so we have to go through this search process, and you can see that you get this very useful information, right? The validation accuracy for that trial, the last one was 0.85, but the best one that was seen throughout the process was 0.89. And that's what you're looking for, like which hyperparameters gave me the best possible result. Something else I want to add is that here we are trying to maximize because it's accuracy rather than minimize. And you don't have to be worried about these. So for these typical evaluation metrics like accuracy versus like mean squared error, Keras is smart enough to know that if you're working with accuracy, you actually want to maximize it rather than minimize it. So you don't have to do anything, and this will be taken care of in the background. So since now we have performed the search and the search is completed, now we can use tuner and then this method, which is get best hyperparameters. In general, you can choose the multiple top performing models, but let's say here we focus on the only or the number one top model that you have. That's why you see a num trials equals 1. And here we print those parameters. So you can see that, the number of hidden units is 320. That seems to be the best one. And the best learning rate is 0.001 or 10 to the negative 3. So that's the result of our hyperparameter tuning without checking all possible configurations using this hyperband method, which we eliminate the ones that they don't perform very well early on. And then the other thing you can do is that now you can use this tuner.hypermodel.build with your best hyperparameters, right? So this is what we get here to actually create this best model, right? With this number of hidden units and learning rate. And something that we want to do is that in general, there's no guarantee that if you choose more epochs, you always get better results. So we set the number of epochs to 50, but we're going to see that actually where that maximum accuracy for the validation data happens. So that's what this line is doing, right? It's saying that like, let's run this 50 times or 50 epochs and see at which epoch the maximum happened. So here, again, I ran this already because this, takes some time. But you can see that it seems that the best epoch actually happened at 22, and after that, the accuracy went down a little bit. So that's now we're going to choose as our final, tuned model in this case, right? So we're going to say that we're going to use this hyper model. We build it using the best hyperparameters, and we run it for this number of epochs. And then again, we run this model, we train it, and then we evaluate it using the test data that we have never used before. So remember, we have not used this test data before until this stage to see what the actual accuracy is on some unseen test data. So here we go through the 22 epochs, and you can see that at the end, the one that we really want to know is the test accuracy, which is very much what we expect, is 0.89. And the test loss, this is like that, cross entropy loss is also relatively close to 0, is 0.38. So this means that in this case, we didn't have to manually do trial and error to find the best configuration. We can actually use a method called Hyperband to do this. And you can, convert this code to Bayesian optimization in particular to see how that, also performs here. But you can see the basics here, right? The most important steps are defining this tuner using either kt.hyperband or kt.bayesian optimization. You provide your hypermodel, and then you perform tuner.search. And after this, you can get the best hyperparameters, the top performing models, and so on. I hope you found this video helpful.